Hello and welcome. In this video, we'll be diving into the world of logarithms and their powerful application in solving exponential equations. By the end of this session, you will be able to use the rules of logarithms to solve complex exponential equations and apply these skills to solve real-world problems involving exponential growth and decay. Let's get started. First, let's quickly recap the essential rules of logarithms that we'll be using today. These rules are the key to unlocking exponential equations. The first rule is the product rule. The logarithm of a product is the sum of the logarithms. So, log base a of x times y is equal to log base a of x plus log base a of y. Next is the quotient rule. The logarithm of a quotient is the difference of the logarithms. Log base a of x divided by y is log base a of x minus log base a of y. And finally, the power rule. This is the most important one for solving exponential equations. The logarithm of a number raised to a power is the power times the logarithm of the number. Log base a of x to the power of p is p times log base a of x. Remember these three rules. They are the tools we'll use to bring the unknown exponent down to a solvable level. Let's start with a worked example. We want to solve the equation 3 times 2 to the power of x equals 5 to the power of x minus 1. Our goal is to find the value of x. Notice that the unknown, x, is in the exponents on both sides of the equation. When the unknown is in the exponent, taking logarithms of both sides is a great strategy. It allows us to use the power rule to bring the exponents down. So we'll take the logarithm of both sides. You can use any base, but the natural logarithm, ln, is often convenient. Now let's use our logarithm rules to simplify. On the left side we have a product, so we use the product rule. This gives us ln of 3 plus ln of 2 to the power of x. On both sides, we can now apply the power rule to bring the exponents down as factors. The x comes down from the exponent of 2, and the entire expression x minus 1 comes down from the exponent of 5. This is the crucial step that makes the equation solvable. Now we have a linear equation in terms of x. Our next step is to expand the brackets and gather all the terms containing x on one side of the equation. Expanding the right side gives us x times ln of 5 minus ln of 5. Let's move the x terms to the right and the constant terms to the left. We add ln of 5 to both sides and subtract x times ln of 2 from both sides. Now that all the x terms are together, we can factor out x. Factoring out x on the right side gives us x times the quantity ln of 5 minus ln of 2. To isolate x, we just need to divide both sides by the term in the brackets. So, x equals ln of 3 plus ln of 5 divided by ln of 5 minus ln of 2. The question asks for the answer in the form log p over log q. We can simplify our expression using the product and quotient rules in reverse. The sum of logarithms in the numerator becomes the logarithm of a product, ln of 15. The difference of logarithms in the denominator becomes the logarithm of a quotient, ln of 5 over 2. And there you have it. We've solved the equation for x. We took logarithms, used the power rule, rearranged the equation, and simplified the result. Let's try another example. This time, we'll solve an inequality. The number of bacteria in a culture is given by n equals 1,000 times 2 to the power of 4t. We want to find the time t when the population first exceeds 1 million. First, let's set up the inequality. We want the population n to be greater than 1 million. This gives us 1,000 times 2 to the power of 4t is greater than 1 million. Before taking logarithms, it's always a good idea to simplify the equation or inequality as much as possible. We can divide both sides by 1,000. This simplifies our inequality to 2 to the power of 4t is greater than 1,000. Now, we take the logarithm of both sides. Again, we'll use the natural logarithm. This gives us ln of 2 to the power of 4t is greater than ln of 1,000. Next, we apply the power rule to bring the exponent down. The exponent 4t comes down as a factor, giving us 4t times ln of 2 is greater than ln of 1,000. To solve for t, we need to divide both sides by 4 times ln of 2. This is a critical step when dealing with inequalities. We must check if the term we are dividing by, 4 times ln of 2, is positive or negative. Since 2 is greater than 1, ln of 2 is positive. Therefore, 4 times ln of 2 is also positive. Because we are dividing by a positive number, the direction of the inequality sign does not change. So t is greater than ln of 1000 divided by 4 times ln of 2. Now, we can use a calculator to find the numerical value. Calculating this gives us approximately 2.49. This means the population will exceed 1 million after 2.49 hours. The question asks for the time. 2.49 hours is 2 hours and 0.49 times 60 minutes, which is about 29 minutes. So, if the culture started at 8 a.m., the population will exceed 1 million at approximately 10:29 a.m. Let's tackle a more complex equation. We need to solve 3 to the power of 2x equals 4 to the power of x minus 1. Again, the unknown x is in the exponents, so we'll take the natural logarithm of both sides. This gives us ln of 3 to the power of 2x equals ln of 4 to the power of x minus 1. Now, we apply the power rule to bring the exponents down. The exponent 2x comes down on the left, and the exponent x minus 1 comes down on the right. Next, we expand the right side of the equation. This gives us 2x ln of 3 equals x ln of 4 minus ln of 4. Now, we need to gather all the terms containing x on one side. Let's move the x ln of 4 term to the left side. Subtracting x ln of 4 from both sides gives us 2x ln of 3 minus x ln of 4 equals negative ln of 4. Now, we factor out x from the left side. This gives us x times the quantity, 2 ln of 3 minus ln of 4 equals negative ln of 4. To isolate x, we divide both sides by the term in the brackets. So x equals negative ln of 4 divided by 2 ln of 3 minus ln of 4. We can simplify the denominator using the power and quotient rules. 2 ln of 3 is ln of 3 squared, which is ln of 9. So the denominator becomes ln of 9 minus ln of 4, which simplifies to ln of 9 over 4. Our expression for x is now negative ln of 4 divided by ln of 9 over 4. We can also use the property that negative ln of 4 is the same as ln of 1 over 4. This gives us x equals ln of 1 over 4 divided by ln of 9 over 4. This is our exact solution. Using a calculator, we can find the approximate value. X is approximately negative 1.23. Let's look at another type of problem, a disguised quadratic equation. Consider the equation 2 to the power of 2x minus 3 times 2 to the power of x plus 2 equals 0. This doesn't look like a quadratic equation at first glance, but we can make a substitution to reveal its true form. Notice that 2 to the power of 2x can be written as 2 to the power of x squared. So our equation becomes 2 to the power of x squared minus 3 times 2 to the power of x plus 2 equals 0. Now, let's make a substitution. Let y equal 2 to the power of x. Substituting y into our equation gives us y squared minus 3y plus 2 equals 0. This is a standard quadratic equation. We can solve this quadratic equation by factoring. It factors into y minus 1 times y minus 2 equals 0. This gives us two possible solutions for y equals 1 or y equals 2. But remember, we are solving for x, not y. We need to substitute back using our original definition, y equals 2 to the power of x. For our first solution, y equals 1, we have 2 to the power of x equals 1. The only way an exponential function can equal 1 is if the exponent is 0, so x equals 0. For our second solution, y equals 2, we have 2 to the power of x equals 2. This means x must be 1. So the equation has two solutions, x equals 0 and x equals 1. By recognizing the disguised quadratic form, we were able to solve this equation. Let's look at a real-world application. A cup of tea is poured at 98 degrees Celsius. After 2 minutes, it has cooled to 94 degrees Celsius. The difference between the T's temperature and the room temperature of 22 degrees Celsius falls exponentially. We need to find the time it takes for the T to cool to 78 degrees Celsius. First, let's define the temperature difference, which we'll call D. D is the temperature of the T. T minus the room temperature, 22. The problem states that this difference, D, falls exponentially. So we can model it with the equation D equals A times E to the power of negative KT. Here, A is the initial temperature difference, and K is the cooling constant. Let's use the initial conditions to find A. At time t equals 0, the T is at 98 degrees. So the initial difference D is 98 minus 22, which is 76. Plugging this into our model, we get 76 equals A times e to the power of 0, which is 1. So A equals 76. Now our model is D equals 76 times e to the power of negative KT. We need to find K using the second piece of information. After 2 minutes, the T is at 94 degrees. The difference D is 94 minus 22, which is 72. Substituting these values into our model, we get 72 equals 76 times e to the power of negative 2k. Now we solve for k. First, divide by 76. This gives us e to the power of negative 2k equals 72 over 76, which simplifies to 18 over 19. To get the exponent down, we take the natural logarithm of both sides. This gives us negative 2k equals ln of 18 over 19. Dividing by negative 2, we find that k equals negative 1/2 times ln of 18 over 19. Using a calculator, k is approximately 0.0270. Now we have our complete model. D equals 76 times e to the power of negative 0.0270t. The final part of the question asks for the time it takes for the T to cool to 78 degrees. At this temperature, the difference D is 78 minus 22, which is 56. We set our model equal to 56 and solve for T. First, divide by 76. Take the natural logarithm of both sides. This gives us negative 0.0270t equals ln of 14 over 19. Finally, we divide by negative 0.0270 to find T. The time is approximately 10.6 minutes. So, it takes about 10.6 minutes for the T to cool to 78 degrees Celsius. Let's look at one more example, this time involving the change of base formula. We want to solve the equation 9 times log base 5 of x equals 25 times log base x of 5. The problem here is that the logarithms have different bases, 5 and x. We need to get them to the same base. We can use the change of base formula, which states that log base b of a is equal to 1 over log base a of b. Applying this to the right side, log base x of 5 is equal to 1 over log base 5 of x. Now we can substitute this back into our original equation. This gives us 9 times log base 5 of x equals 25 divided by log base 5 of x. To solve this, let's make a substitution. Let y equal log base 5 of x. Our equation becomes 9y equals 25 over y. Now we solve for y. Multiply both sides by y. This gives us 9y squared equals 25. Dividing by 9, we get y squared equals 25 over 9. Taking the square root of both sides, y equals plus or minus 5 over 3. We have two possible values for y. Now we substitute back to find x. Remember, y equals log base 5 of x. So log base 5 of x equals 5 over 3. To solve for x, we convert this logarithmic equation into an exponential equation. The base is 5, the exponent is 5 over 3, and the result is x. So x equals 5 to the power of 5 over 3. For our second solution, y equals negative 5 over 3, we have log base 5 of x equals negative 5 over 3. Converting to exponential form, we get x equals 5 to the power of negative 5 over 3. So our two exact solutions are 5 to the power of 5 over 3 and 5 to the power of negative 5 over 3. This example shows how the change of base formula can be used to solve equations with mixed logarithmic bases. Let's quickly recap what we've learned today. We've seen how logarithms are an essential tool for solving equations where the unknown is in the exponent. The key steps are to take the logarithm of both sides, use the power rule to bring the exponent down, and then solve the resulting linear equation. We also saw how to handle inequalities, disguise quadratic equations, and equations with different logarithmic bases. Now it's your turn to practice. Here are 5 questions for you to work through. Pause the video and give them a try. Here are the questions. Remember to use the techniques we've covered. Welcome back. Let's go through the answers. For question 1, x is approximately 4.58. For question 2, x equals 0 or x equals 2. For question 3, x is approximately 2.29. For question 4, x equals 2. And for question 5, it will take approximately 13.9 years. I hope this video has helped you understand how to solve exponential equations using logarithms. Keep practicing, and you'll master this skill. Thank you for watching.